Section 7.1, Introduction to Systems of First Order Linear Ordinary Differential Equations. This is the last topic of the semester, and the last chapter we're going to cover is the chapter is on systems of first order linear differential equations, and this is section 7.1. This is the introduction. So systems of simultaneous ordinary differential equations arise naturally in problems involving several dependent variables, but each of which is a function of the same single independent variable. So all of these functions depend on the same independent variable, which we're going to be denoting by t, and following the notation in the book, we're going to be using x1, x2, and x3 for the dependent variables, all of which are functions of t. And as usual, derivatives or differentiation with respect to t will be denoted by a prime. So x1 prime is the derivative of x1 with respect to t. All right. If you have an arbitrary nth order differential equation, such as, let's say, this one, okay. If you have an arbitrary nth order differential equation, remember that you can always solve for the nth derivative. So you can always move everything that is not the first derivative to one side, and so that you end up only with y to the nth derivative on the left. And if you had something in front of there, you could divide by it. So literally, you could solve for this, and you could write any arbitrary nth order differential equation like that. So here, meaning you have an expression that has all the other derivatives that are smaller or lower order or degree than that one in the t. So everything else that has all these variables is on the right. Okay, if you have a differential equation like that, you can always, turns out, you can always transform that into a system of differential equations. Your system is going to have n equations. All of the equations is going to be first order differential equations. So you're going to have a system of first order differential equations. And the process for converting an arbitrary nth order differential equation into a system of differential equations is always the same. So whenever we want to convert an arbitrary differential equation into a system, we're going to follow always the same procedure. And here is the procedure. You're going to need n variables. Okay, if the differential equation is of order n, you're going to need n variables. The first variable is going to be x1 equals y. So y, right, is a function that we're trying to find that is a solution of the differential equation. So your first variable in the system, x1, is going to be y. Then x2 is going to be the derivative of y. Then the x3 is going to be the second derivative of y. Then you keep going, so you keep increasing the derivatives. So x4 would be the third derivative, x5 would be the fourth derivative, etc., until you use up all the derivatives that appear on the right hand side. Not that one. Okay, so basically you introduce a new variable for each of these things here except for the t, because the t is an independent variable. So x1 will be y, x2 will be y prime, x3 will be y double prime, etc. until the very last one. Xn is going to be the nth minus 1 derivative. So those are going to be your variables, and then your system is going to be basically all of these, but you're going to write them, you don't want to write them with y, you're going to write everything in terms of x. You want to get rid of the y. The y is not going to be one of the variables in your system. So how you do that? Well, the first equation is going to be, note that if you take this equation right here, x1 equals y, x1 equals y. If you take the derivative on both sides of this is going to be x1 prime equals y prime, but y prime equals x2. So that means this is equal to x2. So then, getting rid of that y prime that is in the middle, your equation becomes x1 equals x2. And now that's an equation that expresses this one after you take the derivative that doesn't have y in it. So that's going to be your first equation. So x1 equals x2. And then you keep doing the same thing for all the other equations. So now take that one. So x2 equals y1. If you take the derivative on both sides, this is going to be x2 prime equals y double prime. But y double prime is x3. So then you get x2 prime equals x3. And that's going to be your next equation in the system. And you keep doing this for all of the equations, all right? And then once you get to the last one, what does that give you? So you keep going, and then xn equals the nth derivative. Now you take the derivative on both sides, it's going to give you xn prime equals the nth derivative of y, but the nth derivative of y is this. This is the expression on the right. Alright, but again, I don't want any y, so I'm going to write it instead of like this, like that. I'm going to replace all the y's with what they are in terms of x. So x1, y is x1, so x1, x2, x3, etc., all the way to xn. Xn is the n minus 1th derivative. And now this is the equation in terms of the dependent variables that were introduced, x1, x2, etc. So then this would be your last equation in your system. So the system is going to be this. That is the process for converting any differential equation into a system of differential equations of first order. We're only going to concentrate in this course we're going to concentrate only on differential equations of order 2 for the most part. So this process is going to be very short for the examples that we're going to be concentrating on. Alright, so let's do this one. It says, just transform these differential equations that are both of order 2 into a system of first order differential equations. Alright, so we're going to first introduce a new variable, x1. Let me see if I can. x1 is going to be the u. Okay, normally is y if the original differential equation is written in terms of y, but this one is written in terms of u, so x1 is going to be u. Then what we do, we take the derivative of that, and then we're going to get x1 prime equals u prime. Oh, the next x2, oh, these one out of ink. The next introduction that we have to make is the derivative of u. Okay, now, okay. And this is, we only have a differential equation of order 2. Really, that's the end of the introduction of the variables. Okay, so these are my two dependent variables, x1 and x2. Then, to write the system, what is it? You take the derivative of that one, is going to be x1 prime equals u prime, but u prime is x2. So there you have your first equation in the system. So in my system, my first equation is going to be x1 prime equals x2. Okay, now you take that one and take the derivative. You're going to get x2 prime equals u double prime. What is u double prime? Well, you're supposed to solve for this one. Solve for u double prime. But how do we solve for u double prime? From here, just move these two things to the other side. If you move them to the other side, you're going to get negative 0.5 u prime plus 2u. Okay, so I'm going to write it here. I'm going to scan this. So this is u, x u2, x2 prime equals u2 prime, which is negative 0.5 u prime plus 2u. Now we write this in terms of x and y, in terms of x1 and x2, which is negative 0.5 u prime is x2, and then u is x1. So that's rewriting everything in terms of x1 and x2. And that's your last equation. So my last equation is going to be x2 prime equals this. And I like writing things in order, so I'm going to write this one first. The order of subscripts. So I'm going to write this one first, minus 0.5 x2. And that's your system. Alright, and that's it. It's not difficult. Let's do another example. So first, introduce the variables. First introduction, x1, that would be the u, because our differential equation is in terms of u. If it was in terms of y, then it would be x1 equals y, which is what we have over there, right? Okay, then the next variable, and we're going to only need two because it's a second order differential equation. The next variable is just going to be u prime. If it was a third order differential equation, then x3 would be u double prime, and so on. Alright, so then, these are the variables. Then take the derivative of this one, on both sides, what you're going to get. You're going to get x1 prime equals u prime, but u prime equals x2. So that means, in our system, x1 prime equals x2. Note that this is really going to be always the same equation. If you look, even in general, that is always going to be the first equation. And if you have more, the first n minus 1 equations are always going to be the same in this process. So, okay, so it's no surprise that our first equation was exactly the same as in the other example. Alright, and then lastly, you take the derivative of this one, so you're going to get x2 prime equals u double prime, but u double prime, we can get it from here by solving for u double prime. So move these two terms right here to the right side. Move them to the other side. So this is going to become negative 1.5 u prime minus u plus 3 sin of t. But we have to write in terms of x1 and x2 only. So this is negative 1.5 u prime. What is u prime in terms of x1 and x2? U prime will be x2. So this is going to be x2. And then minus u. U is x1 plus 3 sin of t. That means this is our last equation in the system. And I'm going to write it here. And again, I like writing in order. So I'm going to write x2 prime equals negative x1 minus negative 1.5 x2 plus 3 sin of t. And that's our system. Now what we would like to do is to go in the other direction. If you have a system of differential equations, convert that to a single differential equation. So here we have this system that has two dependent variables, x1 and x2. Remember, we're assuming that the independent variable is t. It is not, there's no t's in there, it's implicit. But either way, our goal is to transform that into a single differential equation. And you could actually transform it into a single differential equation in terms of x1, or you could transform it into a system of differential equations in terms of x2. So it really depends on which variable you want to eliminate. So they have to really to tell you which one to keep, which one to get rid of. So the instructions in this one is that I want to transform this system of differential equations into a single differential equation of second order in terms of x1. So that means we want to get rid of x2. x2 is a variable we would like to eliminate. Alright, since we want to eliminate x2, what we're going to do is we're going to solve for x2 from one of the equations and plug it into the other equation. And that's it. That's going to get rid of x2. But we have to solve for x1, for x2 from the equation that truly gets rid of it. And not, in this case, not both of them, not both of these equations can be used to solve for x2, because one of them actually gets rid of solves completely for the x2, but the other one doesn't. The one that really solves for x2 is actually the first one. If you try solving for x2 in the second one, you see you run into a problem because you have x2 on both sides, and then if you move this x2 to the other side, you would have this, but then there's no way to really solve for x2 from here, because one is a derivative, the other one doesn't. So if I just wanted to have an expression like this, x2 equals something, I would need to get rid of that derivative. So that's a differential equation. You could integrate, but then you would have an integral. I mean, there's no way to really solve this easily. So the second equation is not the way to go. It doesn't lend itself to solving for x2 easily. So but the first one does. So we're going to solve for x2 from the first equation. If you do that, so you move this to the other side and you divide by -2. Okay, that's simple algebra. So if you do that, you're going to get that x2 equals x1 prime minus 3x1 over 2. Okay, so move that to the left and divide by -2. Oh, I forgot the negative. By -2. And that's what you get. And then you're going to plug this in to the next equation. And that's basically it. You need to do a little bit of algebra to simplify things. Into the second equation. So let's do that. In the second equation, remember, I'm replacing it. Wherever I see x2, I'm replacing it with this. So the left-hand side is going to become x1 prime minus 3x1 over 2 prime. So that will be the left-hand side. Replacing x2 with this. Equals 2x1 minus 2, and then I write that, which is x1 prime minus 3x1 over -2. Oh, and I forgot the -2 from there. Okay. Now let's simplify. This left hand side we have to take that derivative, but this is an easy derivative. This is just x1 double prime minus 3x1 prime, all that over negative 2 equals 2x1. Negative and negative is going to give you positive, and then you can cancel the 2's. You can cancel the 2's, and again, the negative and negative becomes a positive, so you would have plus x1 prime minus x1. Okay, now we're going to multiply both sides by negative 2 to get rid of that. Multiply both sides by negative 2. So this is going to become x1 double prime minus 3x1 prime equals negative 4 x1, multiplying everything by negative 2, minus 2 x1 prime plus 6 x1. And now you would get x1 double prime. I'm going to move everything now to the left hand side, everything. If I move this one, that one is a like term with this one, so I can just combine them. So when I move this, it's going to be plus 2x1 prime, but combined with this negative 3x1 prime is going to be minus x1 prime. And then I can combine these two, negative 4x1 and 6x1, those are like terms. That would be positive 2x1 on the right hand side. But then when you move the positive 2x1 to the left, that's going to become negative 2x1 equals 0. And this converts the system into a single differential equation. And that differential equation, we can solve this if we wanted to. We know how to solve that one. If we wanted to solve that, right? This equation is really easy. How you solve that? That's a linear differential equation of order 2 with constant coefficients. So you start by doing finding the characteristic equation. Then you solve that. So you can easily solve for x1. And once you find x1, but you found, let's say you found something, x1 equals this, blah, then you can use this equation, you plug it in there, and you get x2. You plug that in there, you know what x1 is because we found it, you simplify, and then you get x1 and x2, and that solves the system. That's how you can solve a system with differential equations. We're going to be doing other methods, but this is one way of solving a system with differential equations. So transform everything into a single differential equation with one variable, and then maybe you can solve it. No, this doesn't always work. I wrote here sometimes you can do this. I mean, if the system is simple enough, you can do that. Some systems are just complicated and it's hard to convert them to a single differential equation of order 1. But in this one, it was rather simple. The coefficients are constants. If there's no t's, there's no other complicated stuff. You can do this. And then solve this, plug it into what is x2, and then you're done. You solved your system. Again, I'm not going to solve that because the whole point was to just convert it to a single differential equation. But again, that's one method. Alright, so now let's do this again, but with x2. Meaning I want to solve it, I want to transform this system of differential equations into a single differential equation, but this time in terms of x2. This time in terms of x2. So that means I want to get rid of x1. If we want to get rid of x1, that means you have to solve for x1 from one of the equations, whichever equation actually allows you to solve for x1. In this case, the first one is not going to work because you're going to have x1 and x1 prime. There's no easy way to solve for x1 from there, but using the second one, you can do it. So solve for x1 from the second equation. So solving for x1 here, move the 4x to the other side and divide by 3. You're going to get that x1 equals x2 prime plus 4x2 over 3. And now we're going to plug this in the other equation that we didn't use. So plug this into the other equation, which is in this case the first equation. And let's see what we get. So I'm plugging in the first one. So x1 is this. So x2 prime plus 4x2 over 3 prime equals, and then x1, which is this, so this is going to be x2 prime plus 4x2 over 3 minus 2x2. Now take this derivative. This is x2 double prime plus 4x2 prime, all that over 3 equals x2 prime plus 4x2, all that over 3 minus 2x2. Okay, now you can multiply by 3 everywhere to get rid of that 3, and you're going to get x2 double prime plus 4x2 prime equals x2 prime plus 4x2 minus 6x2. Okay, then combining, moving everything to the left and combining like terms, you're going to get x2 double prime. Moving this to the other side, to the left, you're going to get 4x2 prime minus x2 prime. That's plus 3x2 prime. And then combining these two and then moving it, you're going to get, let's see, when you combine these two, you get negative 2x2, and then when you move it, it's going to become positive. So 2x2 equals 0. And that is the system transformed into a single differential equation in terms of x2. That's it. If we wanted to solve that, again, we know how to solve that because that's a linear differential equation of order 2 with constant coefficients. So you write down the characteristic equation. Using the characteristic equation, you can easily find the solution. And then once you have x2, so using this method, you're going to find x2, and once you have x2, you plug it in there, and you're going to get x1. So that's one way to solve the system.